Hi, this is Miss Logan. Today I'll be covering Chapter 5, which is Newton's Laws of Motion. To begin, a force is a push or a pull. So force is a vector, so it has a magnitude and direction. So shown in this picture, this person is pulling with a force at an angle. So very similar to how we did in kinematics, we need to break this up into the x and y components. It is still a vector. All right, so mass is different from weight. So mass is the measure of how hard it is to change an object's velocity. Okay, it's the amount of matter that's in an object. I like to think of it like that. The weight is going to depend on our gravity, and we'll get to that in a little bit. All right, so Newton's first law of motion. If I stop pushing an object, does it stop moving? So if I had a frictionless surface, it would keep moving on forever until something stopped it. Okay, so if there are no external forces, an object will just keep moving on forever and ever and ever, which is called the law of inertia. All right, so our second law of motion, I'm going to actually derive for you right here. Okay, so we have two different springs, and if I want to pull this object with double the acceleration than my top object, I need to pull it with double the force. This makes sense. If I want to make something go faster, I need to give it more force. Second situation, if I have two different blocks here, so I have one block and then I have two here, if I am pulling with the same force, then my accelerations will be different. This makes sense. If I'm pulling something that's heavier, I'm going to probably go slower unless I need more force. What does this give us? This gives us F equals ma, which is Newton's second law of motion. So two different ways to write it: acceleration equals force over mass, or force equals ma, which is something that we've probably seen before. So Newton's second law is more than F equals ma. It's the sum of all the forces equals mass times acceleration. Now something you'll note is that this arrow right here means that something is a vector. So if I have forces going the x and the y, I need to break this up in the x direction and in the y direction. So down here on this chart, we are going to use our SI units. So for mass, we're going to use kilograms, acceleration meters per second squared, and force, which is a Newton. And in class, we will derive what a Newton actually means. When we talk about Newton's second law, we're also going to talk about free body diagrams. So a free body diagram shows every force acting on an object. So free body diagrams are really something that we practice with time and are able to notice different things. And as I go through this flipped lesson, you will see me create different free body diagrams. The most important part is that we're sketching the forces in the correct directions. Okay. Now, this bottom part here is resolving the forces into components is something that we'll do as we go. We need to also choose a convenient coordinate system so we know which direction things are going. So here's an example of a free body diagram. I'm holding a book. Okay. Now, I only have two forces that are acting on this. What is always acting on us? The force of gravity. Now, what do we have going opposite? And we'll talk about this in a little bit. We have our normal force. Anytime something is supported by something else, we have our normal force. Now, if I was moving my hand to the left, I would also have a force applied right here. All right, so our last law of motion is that forces are coming in pairs. So if object 1 exerts a force on object 2, then object 2 needs to exert a force on object 1. So this is our action-reaction pairs. Okay, so if I'm pushing these two masses along, they're also pushing on each other. Kind of something we don't always think about, but this is constantly going on. Here are some examples of action-reaction pairs. For instance, this person is pushing on the refrigerator, and the refrigerator is pushing back. The car pushing forward, and then there's also pushing back on the wheel and the road. Just a few examples. Now, how do we use Newton's third law in AP Physics? Well, we look at different situations with contact forces. So the contact force is between two objects. Now, the big picture with this is that the force exerted depends on which way you are pushing on two objects. So it's going to be different in this situation when I'm pushing on box 2 compared to in this situation where I'm pushing on box 1. So let's look at an example problem that is going to both integrate Newton's second law and Newton's third law. So box A is 5 kilograms and box B is 3 kilograms. And we have a force of 30 newtons pushing to the right. All right, so what is the acceleration of the box? So I know my force is equal to 30 newtons. My total mass, because I'm pushing 2, is 3 plus 5, which is 8 kg. So I am looking for acceleration, so I want to use Newton's second law. So A equals F over m when I rearrange. So when I plug in my numbers, I will get 30 over 8. So I figured out my acceleration, and I can just leave it in this form. That's fine. Now we're going to look at what is the contact force between box A and B. So I'm looking for force, so let's write that down. Force equals question mark. And I know my acceleration from my previous problem, 30 over 8 meters per second squared. Now, box A is pushing on box B. So the mass that we're going to be using is 5 kg. And that's the mass that's pushing on the other one. So I can just use F equals m times A. And when I plug in my numbers, I will get, let me just do this real fast, 18.75 newtons. Okay, so at the beginning of this lecture, I talked a little bit about how forces are vectors. Okay. Now, for the remaining sections, we'll do some problems in class to really apply all of this knowledge. So anytime I have a force that is in 2 dimensions, I need to break it up into x and y, the same exact way that we did in kinematics. Now, one important concept that we have to remember is weight. So mass does not equal weight. This is one of the biggest misconceptions that we have, because in real life, we often use these two things interchangeably. So the definition of weight is weight equals mass times gravity. So if I'm standing here as a person and I have a mass of 80 kg, I need to figure out my weight. I would take my mass of 80 kg and multiply by 9.8, which is gravity. This would give me, in newtons, how much I weigh. Now, one concept that is really important in physics is that our apparent weight. Now, because we have contact forces going out, our weight might not actually be what it seems in different situations. So the perception of my weight is based on the contact forces between your body and your surroundings. So if we're just standing on Earth, our weight is just W equals mg. However, if my surroundings are accelerating, my apparent weight is going to be more or less. So in this case, this person is accelerating up and their weight is going down. So what is this going to look like? Well, my weight is my mass times gravity. However, we also have our apparent weight, which is going in the opposite direction. So we have mass times some acceleration. Now, if my weight is going down and my apparent weight is going up, I'm going to have to subtract these two. All right, so last we're going to talk a little bit about normal forces, and this is the portion where we're really going to be exploring these problems in class together. So a normal force is exerted by a surface of an object. So my object has to be sitting on something else. If I have a ball flying through the air, there's no normal force. But if my ball is sitting on a desk, I do have normal force. One of the things that we'll be working on is how can I use normal force and weight to help me solve problems. So my normal force, if something is still, is equal to my weight. It's just sitting still. However, if something is moving, my normal force may be different. And this is when we get into things that are moving at an angle. Another important part that will help us solve some problems in class is that the normal force is always perpendicular to the surface. So in this instance, I have force normal at this angle. However, I have some other things going on. I have my weight going down. So you'll notice that this actually creates an angle. What do we need to do to this? Well, we're actually going to switch our coordinates so they're at an angle. This is really the only time in physics where we're switching our coordinate system to be at an angle. So now I can break up my weight into my x and my y components. All right, so we will be doing a lot of problems in class with normal forces and setting up these problems. They do take some time and a little bit of explanation, so I'd like to do it in class. So make sure you've taken notes during this flipped lesson, and please take the form and come prepared to class.